Something's happening at the edge of our solar system that has NASA scientists watching their monitors around the clock. An object from another star system, a visitor from the cosmic void between galaxies, just did something it absolutely wasn't supposed to do. After swinging past the sun and beginning its journey back into the darkness, this interstellar comet started glowing brighter. Not dimmer, like every model predicted. Brighter. And it's still getting more intense. The week leading up to perihelion, the point of closest approach to the sun, saw observation efforts reach a fever pitch. This was it, the moment when the comet would receive maximum heating, when outgassing would peak, when the tail would reach its most spectacular development. Every telescope that could observe near the sun without damaging its instruments was positioned and ready. Space-based observatories that could block the sun's direct light, prepared to watch the comet's final approach and swing around our star. Ground-based observers had a narrower window. The comet would be too close to the sun in the sky for safe observation during the actual perihelion passage, lost in the glare. But in the hours before and after, there would be opportunities to catch it in twilight, a ghostly presence near the horizon. The truly valuable data would come from solar observatories and space telescopes designed specifically to study the sun's corona, instruments that could observe the comet even when it was apparently right next to the solar disk. The predictions were refined down to the minute. Perihelion would occur at EO 347 UTC on a Wednesday morning, with the comet passing just 0.12 astronomical units from the sun's surface, about 18 million kilometers. Close enough for intense heating, far enough to avoid complete destruction, assuming the nucleus was sturdy enough. Some scientists worried it might fragment, unable to withstand the thermal stress. The nucleus size estimates ranged from 3 to 7 kilometers across. Decent size, probably solid enough to survive. Probably. As the comet dove toward its closest approach, the activity ramped up exactly as models predicted. The coma expanded, glowing brighter as more material vaporized from the nucleus. Jets of gas erupted from specific points on the surface, where sunlight hit volatile, rich areas, creating pinwheel patterns as the nucleus rotated. The tail stretched across millions of kilometers, a magnificent banner of ancient ice, vaporized and ionized, fluorescing in the solar ultraviolet radiation. It was textbook comet behavior, beautiful and exactly what you'd expect, the came perihelion itself. The solar coronagraph images captured the comet's passage, a bright smudge moving against the structured chaos of the sun's outer atmosphere. Scientists watched in real time, or as real time as data transmission allowed, holding their collective breath. Would it hold together? Would they see a sudden brightening that indicated fragmentation? The images streamed in, processed rapidly by automated systems, displayed on screens in control rooms and research centers around the globe. It survived. The comet emerged from perihelion intact, no obvious fragmentation. Still a single bright object rather than a scattered debris field. The relief among the scientific teams was palpable. An intact nucleus meant better data, clearer observations, a more complete picture of this interstellar visitor's composition and structure. The post-perihelion observation phase could proceed as planned, watching the comet fade as it climbed back out of the inner solar system and headed toward its eventual exit from our cosmic neighborhood. The first 24 hours after perihelion looked perfect. The comet appeared in evening twilight for observers in the southern hemisphere, a spectacular sight hanging above the horizon with its tail pointing away from the sun. Brightness measurements showed the expected peak, intensely bright from all the activated volatiles, outgassing at maximum rate from the heat it had absorbed. Spectroscopy teams worked overtime analyzing the emission lines, cataloging every element and molecule they could identify in the coma and tail. The data was pristine, better than anyone had hoped. Day 2 post-perihelion continued the nominal pattern. Brightness declining slightly, exactly as predicted. The comet was moving away from the sun now, the heating intensity decreasing, outgassing starting to slow down, everything following the textbook progression. Research teams began preliminary analysis of the perihelion data, writing up initial findings, comparing observations to pre-perihelion models. The mission, if you could call an observation campaign a mission, was being declared a complete success. Day 3 showed the first hint that something was off. A brightness measurement from an automated survey telescope came back higher than expected, just slightly, within the margin of error, really. The astronomer who noticed it almost dismissed it as instrument calibration drift or atmospheric effects. But protocol said to flag anything unusual, so it got noted in the observation log. Nobody paid much attention. Comet brightness fluctuates. Everyone knows that. It's rarely a smooth curve. Day 4 brought more anomalous readings. Multiple telescopes now reporting brightness levels that didn't quite match the predicted fade. Still not alarming, still within the realm of normal comet variability, but enough that people started paying closer attention. Additional observations were scheduled to nail down exactly what was happening. Maybe there was a delayed outburst, a pocket of volatile material that had taken time to heat through and was now vaporizing. It happens sometimes, still interesting, still worth documenting, but not concerning. Day 5 made it clear something genuinely unusual was occurring. The comet wasn't fading. In fact, it appeared to be brightening again, slowly but measurably. The photometry data from multiple independent sources all agreed. This wasn't instrument error or atmospheric effects. The comet, now millions of kilometers farther from the sun than it had been at perihelion, was producing more light than it had the day before. That wasn't supposed to happen. Emergency observation requests went out. Telescopes that had been reassigned to other projects were asked to make room for additional comet measurements. Scientists who had moved on to analyzing the perihelion data found themselves scrambling back to active observation mode. The initial assumption was that they were witnessing a delayed fragmentation event, the nucleus finally breaking apart from thermal stress, creating fresh surface area and releasing trapped volatiles. It was unusual for fragmentation to manifest this way, but it was the most logical explanation, except the high-resolution images didn't show fragmentation. The nucleus, as best they could resolve it, still appeared to be a single object. No obvious debris cloud, no separation of distinct fragments, just one solid chunk of interstellar ice and rock, glowing brighter than it had any right to be. The spectroscopy started showing changes too. Subtle shifts in the emission lines that suggested the composition of the outgassing material was different than it had been during perihelion. More complex organics appearing, molecular species that required specific conditions to form. Conditions that shouldn't exist in the cooling environment of a post-perihelion comet. By day 7, the brightening was undeniable and unprecedented. The comet was now visibly brighter than it had been at its predicted peak, and the trend was continuing upward. The minor scientific curiosity had become a major mystery. Papers in preparation had to be completely rewritten. Models were being torn apart and rebuilt to try to explain this behavior. Theories proliferated, each trying to account for a comet that was violating basic assumptions about how these objects work. The astronomy community wasn't just puzzled anymore. They were genuinely concerned that they were missing something fundamental. A comet brightening after perihelion, after moving away from its primary heat source, suggested an internal energy process that standard comet models didn't account for. The brightening rate accelerated through the second week post-perihelion, reaching 40% above the predicted peak brightness. In comet terms, this was off the charts weird. Teams went back through historical records, searching for any precedent. There were cases of comets showing outbursts, sudden brightness increases from various causes. But those were typically short-lived events, brief flare-ups that faded within hours or days. This was different, a sustained, increasing brightness over more than a week and still going. The closest historical parallel anyone could find was Comet Schwarzmann-Wachmann 1, known for periodic outbursts, but even that wasn't really comparable. This was new territory. The first detailed analysis suggested the brightening was primarily coming from increased particle emission rather than just gas. The dust production rate had apparently gone up significantly, creating a denser coma that reflected more sunlight. But why would dust production increase as the comet moved away from the sun? Dust is released when ice vaporizes, carrying embedded particles with it. Less solar heating should mean less vaporization, less dust, unless something inside the comet was generating heat independently of solar radiation. That realization shifted the entire investigation. If the comet had an internal heat source, what could it be? The obvious answer was radioactive decay. But the levels required to produce this much activity would mean the nucleus was loaded with radioactive elements far beyond what any natural process should create. Some researchers floated the idea cautiously, knowing how controversial it would be. Others pushed back hard, arguing there had to be a more conventional explanation. The alternative theory involved a cascading crystallization process. Comets contain water ice in amorphous structure when they form in the extreme cold of interstellar space. When warmed, this amorphous ice can suddenly crystallize, releasing heat in the process. If perihelion had triggered a delayed crystallization wave working its way through the nucleus interior, it could theoretically generate enough heat to sustain outgassing even as solar heating decreased. The math was tricky, and it required some generous assumptions about the nucleus structure, but it was at least physically plausible without invoking anything exotic. But that theory had problems too. The amount of amorphous ice required, the specific thermal properties needed, the timing of the crystallization wave, it all had to line up perfectly. And it didn't explain the spectroscopic changes, the appearance of organic molecules that suggested chemistry happening inside the coma that shouldn't be occurring. The crystallization hypothesis became one of several competing ideas, none of them entirely satisfactory. Then came the morphology changes. High-resolution imaging revealed that the coma structure was evolving in strange ways. Instead of the relatively symmetric glow expected from a rotating nucleus with active areas, the coma was developing distinct jets and streams that appeared and disappeared over timescales of hours. Some of these features seemed to move in ways that didn't match the nucleus rotation rate calculated earlier. It was as if the object was venting gas from areas that turned on and off independently of solar heating, controlled by some internal process. One particular jet caught everyone's attention. It persisted for 3 days, pointing in a consistent direction relative to the background stars, not rotating with the nucleus. The thrust from this jet was strong enough that orbital mechanics teams calculated it might actually be affecting the comet's trajectory slightly. Not much, just a tiny delta V change, but measurable. A self-propelled comet, essentially, driven by its own outgassing in a direction that seemed almost deliberate. That observation sparked the conversation nobody really wanted to have publicly. Could this object be artificial? The question had been lurking in the background since Oumuamua exhibited its anomalous acceleration back in 2017. That earlier interstellar visitor had shown non-gravitational acceleration that some scientists, notably Harvard's Avi Loeb, had suggested might indicate artificial origins. The mainstream astronomy community had pushed back hard against that interpretation, but the questions had never fully gone away. Now, here was another interstellar object showing bizarre behavior, and the whispers started again. Most scientists remained firmly in the natural phenomenon camp. Space is weird, comets are unpredictable, and just because we don't understand something immediately doesn't mean we should jump to extraordinary explanations. The data would eventually make sense within known physics and chemistry. It always did. The artificial hypothesis was seen as a distraction, the kind of speculation that played well in media but didn't advance actual understanding. But a few researchers, quietly, started looking at the object with fresh eyes. What if you assumed it wasn't entirely natural? What would you look for? Radio emissions at specific frequencies? Geometric patterns in the outgassing? Anomalies in the light curve that suggested structure rather than random activity? These investigations were done carefully, without press releases or premature announcements. Nobody wanted to be the person crying alien spacecraft without absolutely bulletproof evidence. The radio observations found nothing obviously artificial. No narrowband signals, no modulation patterns, no repeating sequences. Just the normal radio emissions from ionized gas in the coma. Exactly what you'd expect from a comet. The optical observations showed variability, but nothing that screamed geometric or designed. The nucleus, to the extent it could be resolved, looked lumpy and irregular like most comet nuclei. If this was a spacecraft, it was doing an excellent job of looking like a natural object. By the end of the second week, post-perihelion, the comet's brightness had increased by nearly 60% above the predicted peak. The sustained brightening had become the primary focus of observation efforts worldwide. Every available instrument was being pointed at this object whenever it was above the horizon. The data was accumulating rapidly, but understanding wasn't keeping pace. For every question answered, two more emerged. The public attention intensified. News organizations picked up on the mystery, running stories about the bizarre interstellar comet that was defying scientific predictions. Most coverage was responsible, interviewing astronomers who explained the various natural hypotheses being explored. But the fringe media had a field day, declaring it everything from an alien probe to a harbinger of cosmic disaster. Social media discourse ranged from informed discussion to wild conspiracy theories. The hashtag Interstellar Comet trended globally. NASA found itself in the position of having to issue public statements. Yes, they were monitoring the object carefully. Yes, the behavior was unusual and not fully explained yet. No, there was no evidence of artificial origins. No, it didn't pose a threat to Earth. The trajectory was well understood. The closest approach to Earth's orbit had already been calculated, and there was no danger. The statements were carefully worded to be reassuring without dismissing the genuine scientific mystery at play. But internally, the conversations were more concerned. Not about alien spacecraft or imminent danger, but about the uncomfortable realization that there were aspects of comet behavior, especially for interstellar objects, that weren't understood as well as everyone had assumed. If this comet could surprise them so completely, what else might they be missing? What other assumptions about these objects might be wrong? The decision to issue a formal alert came during a high-level video conference that included representatives from NASA's Planetary Defense Coordination Office, the Jet Propulsion Laboratory, the Space Telescope Science Institute, and several university research teams. The meeting had been called to assess the latest trajectory data and brightness measurements, but it quickly became clear that the situation warranted more formal communication protocols. The concern wasn't about imminent danger. Everyone in the meeting agreed the collision risk remained negligible. But the object's unpredictable behavior meant uncertainty in future trajectory predictions was higher than normal. The non-gravitational forces from asymmetric outgassing were measurably affecting the orbit, and until the mechanism driving that outgassing was understood, precise long-term trajectory forecasting was difficult. That uncertainty, combined with the object's interstellar origin and anomalous characteristics, justified elevated attention. The alert went out through established channels: the International Astronomical Union's Minor Planet Center, the Space Situational Awareness Network, space agencies in partner nations, and select research institutions with relevant observational capabilities. The language was carefully crafted to convey appropriate concern without triggering panic. The object was described as under enhanced monitoring due to anomalous post-perihelion behavior and trajectory uncertainty introduced by non-gravitational forces. Media picked up on the alert within hours. NASA issues. Warning about interstellar comet ran the headlines, with varying levels of accuracy in the details. Most mainstream outlets got the story reasonably correct, explaining that scientists were monitoring an unusual object, but that no threat to Earth existed. The tabloid press predictably went for more sensational angles, with some claiming the comet was on a collision course, and others reviving alien spacecraft theories. NASA's Public Affairs Office went into overdrive, arranging press briefings and interviews with astronomers who could explain the situation in accessible terms. The message was consistent. This is a fascinating scientific mystery. We're actively studying it. There's no danger to Earth. And the alert is a standard precautionary measure. Most of the public response was curiosity rather than fear, with people asking how they could see the comet themselves and what the latest observations showed. Behind the public messaging, the technical response intensified. JPL's Center for Near-Earth Object Studies assigned additional personnel to maintain updated orbital solutions, incorporating new observations as they came in. The Goldstone and Arecibo radar facilities, typically used for asteroid characterization, attempted to bounce signals off the comet's nucleus to get precise size and rotation measurements. The radar returns were weak due to the distance and the obscuring coma, but they provided some useful data about the nucleus structure. Space-based assets were reoriented to maximize observation time. The Hubble Space Telescope cleared time in its schedule for high-resolution imaging and spectroscopy. The James Webb Space Telescope, with its infrared capabilities, was tasked with thermal measurements that could reveal temperature distributions across the coma and potentially characterize the nucleus composition. Every major facility that could contribute something unique to understanding C-2024X1 was brought into the Coordinated Observation Campaign. International cooperation reached levels rarely seen outside of major planetary missions. ESA's facilities in Chile provided continuous monitoring during times when the object was below the horizon for North American observatories. JAXA contributed analysis expertise and coordinated observations from Japanese telescopes. Russia's space agency shared data from their monitoring systems. China offered time on their new large aperture telescopes. The global astronomy community came together with remarkable efficiency, united by the scientific importance and the practical need to understand this object's behavior. Amateur astronomers played a surprisingly important role. With hundreds of sophisticated backyard observatories around the world, the amateur community could provide continuous coverage that complemented professional facilities. While they couldn't match the sensitivity or spectral resolution of major telescopes, amateur photometry provided valuable data points for tracking brightness variations on short timescales. Several amateur groups organized coordinated observation campaigns, filling gaps in the professional monitoring network. The data pipeline had to be upgraded to handle the volume of observations streaming in. Terabytes of images, spectra, and photometry measurements needed to be collected, calibrated, analyzed, and shared among research teams. NASA stood up dedicated servers to host the C-2024X1 database, making all observations publicly available within hours of acquisition. Open data access was crucial for enabling rapid analysis by the global research community, ensuring that discoveries weren't delayed by bureaucratic data-sharing processes. Analysis teams working with machine learning tools began searching for patterns in the vast dataset. Could AI algorithms identify subtle correlations between outgassing events and other observable parameters? Were there periodic signals buried in the brightness variations that might reveal rotation rates or internal structure? The machine learning approaches found some interesting candidates, features in the data that warranted human investigation, but nothing that immediately cracked the central mystery. 4 weeks post-perihelion, the comet's brightness peaked at 94% above the predicted maximum, then finally began to level off. The rate of increase slowed, then stopped, hovering at this elevated level for 3 days before starting a gradual decline. The brightening phase appeared to be over, at least for now. The collective relief among scientists was tempered by the knowledge that they still didn't really understand what had caused it. The leveling off behavior provided crucial data for distinguishing between hypotheses. Models based on crystallization predicted a gradual decline after the crystallization wave exhausted available amorphous ice. Models based on volatile pocket exposure predicted more sporadic behavior, with brightness fluctuating as different pockets were exposed and depleted. Models based on radioactive heating predicted sustained activity at a relatively constant level. The observed pattern of peaking and then slowly declining fit the crystallization model best, though not perfectly. But just when scientists thought the comet was settling into more predictable behavior, the morphology threw another curveball. The jet structure in the coma reorganized dramatically over a period of just 6 hours. What had been multiple small jets consolidated into 2 large, well-defined streams of material, pointing in nearly opposite directions. The symmetry was striking, almost too perfect. Images showed the nucleus at the center, with 2 brilliant jets extending millions of kilometers in opposite directions, the whole structure looking almost artificial in its geometric precision. Researchers scrambled to explain the sudden reorganization. The leading theory involved the nucleus beginning to split, fracturing along an internal weakness plane with active areas on each fragment, creating the opposed jets. But high-resolution images didn't clearly show 2 separate bodies, just the single nucleus with these remarkable outflows. Maybe the split had just started, with the pieces still close together, or maybe the jets were coming from opposite sides of a single nucleus with a very specific rotation axis alignment. Neither explanation felt entirely satisfactory. The opposed jet configuration had important implications for trajectory predictions. Thrust from outgassing was now more balanced, with forces from the 2 jets partially canceling out. This should reduce the non-gravitational acceleration that had been making orbital calculations uncertain. Trajectory analysts updated their models with the new jet geometry and found that orbit predictions became more stable, with tighter error bounds on future position estimates. That was good news for planetary defense considerations, even if the underlying physics remained mysterious. Public interest surged again with the new jet images. They were visually spectacular, the kind of astronomical photography that made front pages and went viral on social media. NASA released enhanced color versions showing the nucleus as a bright point, with the magnificent opposed jets streaming away. The images drew comparisons to everything from cosmic butterflies to starships in science fiction. For a few days, C-2024-X1 dominated the cultural conversation, becoming that rare astronomy story that broke through to mainstream awareness. Educational opportunities flourished. Planetariums created shows about the interstellar visitor. University physics departments offered public lectures explaining what was known and unknown about the object. Online astronomy communities organized observation parties, gathering in dark sky locations to view the comet through telescopes. The event became a teaching moment about scientific process, showing how researchers deal with unexpected observations and refine understanding through systematic study. Congressional interest picked up too, in ways that made NASA administrators nervous. Some legislators wanted hearings about whether the agency was adequately prepared to track and respond to unusual objects entering the solar system. Others asked pointed questions about whether NASA was being fully transparent about what they knew, with implications that maybe more concerning information was being withheld. The questions reflected genuine constituent curiosity, but also suspicion fueled by fringe media speculation. NASA leadership had to walk a careful line, being open about the scientific uncertainties while pushing back against conspiracy theories. They released comprehensive technical reports detailing everything known about C-2024-X1, holding nothing back except some specific observational data that was still being calibrated and validated. The transparency was important for maintaining public trust, showing that scientists were genuinely puzzled rather than hiding alarming discoveries. Funding conversations started happening in parallel. This observation campaign was expensive, consuming telescope time, staff hours, and computational resources across multiple agencies and institutions. Some of it could be covered by existing planetary defense and astronomy budgets, but a sustained multi-month effort would require additional resources. NASA requested supplemental funding specifically for C-2024 X1 research and monitoring, arguing that an opportunity to study an interstellar object this thoroughly might not come again for decades. The request moved through the budget process with unusual speed. Even fiscally conservative legislators recognized the scientific value and the public interest in understanding this cosmic visitor. The supplemental funding was approved with bipartisan support, one of the few space-related expenditures in recent years that generated almost no opposition. The money allowed NASA to maintain dedicated monitoring, support international collaboration, and fund rapid analysis of incoming data. 5 weeks post-perihelion, the coordinated monitoring had settled into a sustainable rhythm. Observatories worldwide had established schedules maximizing coverage while balancing other scientific priorities. The data pipeline was humming efficiently. Analysis teams had developed specialized workflows for the various types of measurements. The initial crisis atmosphere had evolved into something more like a long-term research program, still intense but organized and methodical. The trajectory uncertainty had decreased significantly with the more stable jet configuration. Updated orbital calculations showed that C-2024 X1 would reach its closest approach to Earth's orbital path in approximately 11 weeks, passing at a distance of 0.29 astronomical units, with an error margin now tightened to plus or minus 0.003 AU. Still comfortably safe, with the refined predictions allowing planetary defense teams to reduce their alert status slightly. But everyone knew the comet could surprise them again. It had already defied predictions multiple times. The conservative approach was to maintain vigilant monitoring, regardless of what models S